So now it's time to apply what we just learned about solutions to stoichiometry. Now, just as a reminder, all good stoichiometry problems essentially do one very similar thing. You start off with moles of one substance, and then through mole-to-mole ratios, you relate it to moles of a second substance. It's essentially like transferring one material out for another. Now, unfortunately, in the lab, we don't have any tools that can directly measure moles. So we have only certain types of measurements, which we then have to convert into moles. Most commonly, what we usually use is grams. We have balances that can measure grams. But unfortunately, we just learned about solutions, which don't really work well with balances. We measure those in the unit of liters. In either case, we have a way of converting those two measurements into moles. And in like manner, on the flip side of the stoichiometry problem, once we've actually calculated the number of moles of the material we're looking for, we need to be able to convert that back out into a usable measurement, something I can go and actually measure in the lab, whether that be grams or liters. One thing that is absolutely 100% possible is that molarity can actually be used as a conversion factor. Because it relates the number of moles and the number of liters, we can actually use this to either convert moles into liters or liters into moles. I want to show you what I'm kind of talking about here. So again, if we just simply use this conversion factor, you can kind of see if I put liters in front of it over 1, my measurement over 1, as we normally do in a stoichiometry problem, the unit of liters would actually cancel out, leaving you with moles in the top last box, effectively converting your measurement liters into the unit of moles. In like manner, if I use the inverse of molarity, now you can see I have liters on the top and moles on the bottom. If I had a number of moles and wanted to convert it into liters, now my moles would cancel out, leaving me with liters on the top, effectively converting backwards from moles back into liters. Now this is extremely helpful when I'm doing a stoichiometry problem, because at the beginning and at the end of a stoichiometry problem, I'm going between a measurement and a number of moles. Time for an example problem. Let's take a look at this one. If we have 0.75 liters of 1.5 molar copper 2 nitrate, and we're reacting that with an excess of solid zinc, how many grams of solid product could actually be produced? Well, hopefully you're saying in your head right now, well, all good stoichiometry problems start off with the exact same thing, a balanced chemical equation. And in like manner, it's really important to make sure that you take the information given about every chemical in that problem and layer it underneath, so you can see what you're dealing with. In this case now, I have a very clear path forward. I know that I'm probably going to have to start with this copper 2 nitrate since it's the only information that I have everything given, and I'm being asked about grams of copper, so now I have a destination and endpoint. Time to start our stoichiometry problem. I'm going to start off with the measurement part of the two pieces of information there. And that can be confusing when you're dealing with solutions, because you'll have two pieces of information given. Never start with the molarity. Always start with the measurement of liters. Let's put that directly into our stoichiometry problem. So 0.75 liters over 1. And then, of course, those liters are going to fall down to the bottom of the next box. And I want to convert that into moles, since that's usually the second step of a stoichiometry problem. And boy, would it be nice if I had that relationship between the moles and the number of liters. I wonder where I could find that. Why, look, it's the molarity. And that's actually given to us in the problem. So now I just need to use this and layer it into my problem. Now, if my solution is 1.5 molar, what that means is I have 1.5 moles for every 1 liter of solution. So now I have some numbers I can just plug and chug in, 1.5 moles to every 1 liter. And now we can proceed like normal through our stoichiometry problem, where the moles are going to cross down to the bottom of the next box and be replaced with the chemical that I'm looking for, moles of copper. Don't forget that the numbers from the mole-to-mole ratio come from the coefficients from the balanced chemical equation, in this case 1 to 1. And now I can convert my moles back into grams by using the molar mass. Time to plug and chug, and you'll find out that we have 71 grams of copper to be expected. Let's try another sample problem, a little bit different this time. Very similar to our last problem, but with a little bit of a twist. So if we have 0.75 liters of 1.5 molar copper 2 nitrate, and again we're reacting that with an excess of zinc, now the question is asking us, what is the molarity of the aqueous product? Like every good balanced chemical equation, is a really great place to start and layer the information that you're given. Now in this problem we have a similar starting point, but we're going to have a little bit of a different ending point. And one thing that's really important to note here is that if we're asked to calculate the molarity, you're going to need to know the volume that the solution is in. Now in order to make the product, I have to take these two reactants and mix them together, and we're really looking for that liquid volume. Now luckily, the one thing is a solid, so it doesn't take up any liquid volume, but the second thing has 0.75 liters. That 0.75 liters is going to be consistent from the beginning to the end of the problem. So if I need to know the volume at the end of the problem, it's going to be exactly the same. And I can actually just put that in the second part of my equation, 0.75 liters. Now if I'm asked to calculate the molarity, remember that again, molarity is moles over liters. So I would actually need two numbers to be able to solve this problem. And I already know one. I know that my final product is in 0.75 liters of solution. So now how am I going to get the moles part? Goodness gracious. I am thinking that maybe stoichiometry might be the answer. Let's start off with the amount of the reactant that we know that we have, the 0.75 liters, since that again is the measurement of the material that we know. And let's convert it into moles the same way that we did before. Let's exchange liters for moles. And don't forget, where do I get that information from now, that relationship between moles and liters? That's the molarity, 1.5 moles for every 1 liter. And I can continue forward, exchanging my moles of copper 2 nitrate for moles of zinc 2 nitrate. Mole to mole ratio still says 1 to 1. Now I don't want to go any further with my stoichiometry problem here, because again, I'm looking for moles. Moles is in my top last box, so I'm going to plug and chug right from here. That gives me the amount of 1.1 moles of zinc nitrate, and I can plug that into my problem. So my 1.1 moles goes on the top, my 0.75 liters goes on the bottom, and that will give me my final answer of 1.47 molar for my aqueous product. Again, the biggest thing here to remember is that when you're doing the chemical reaction, if they ask you about the molarity on that product side, that number of moles is in the total volume of solution. So if you're given more than one liquid at the beginning, simply add together those volumes, and that'll be your final volume that you plug in for that molarity problem. Let's talk about a couple problem twists and a couple reminders that are going to make your lives a little bit easier. All right, so taking back a look at this same stoichiometry problem that we had, there were a couple key words that were really important to kind of remember. First of all, the word excess. Remember that the word excess in chemistry generally means ignore this for calculations. What that really means for this problem is that we really only have one starting point and one ending point, which means one stoichiometry problem. And I would use the information that I'm given about the one reactant as my starting point, and then the material that I'm asked about is going to mark my end point. Well, what if we didn't have this word excess here? What if it was replaced with an actual number, like 5 grams? Well, now I'm really confused about where to start a singular stoichiometry problem. This is the indication that you have a limiting reactant problem, because now you have two starting amounts that you can actually start from. That implies two stoichiometry problems. One stoichiometry problem would start off with the 5 grams, and another stoichiometry problem would start off with the 0.75 liters. Both would end up calculating to the same ending point, the zinc nitrate. Final little twist here. Let's go back to the original problem where we have an excess and only one stoich problem to think about. Sometimes the problem will have an add-on at the end where it asks you, what is the percent yield? Well, don't forget that percent yield is actual yield over theoretical yield. Theoretical yield is the one that you calculate through stoichiometry. An actual yield has to be given to you either in the problem if you're only working on paper, or you actually have to go to the lab and do that reaction to get that actual yield. This I thought you might like. This is a little stoichiometry mashup, a way that I like to kind of envision and plan my stoichiometry problem. The information on the left-hand side would be the information that you're given in the problem, and then the information on the right-hand side would be the information that you were asked for in the problem. Well, let's say that the material that they give me starts off as a solid. Well, if I'm going to start my stoichiometry problem, there's a very defined path forward where I would use the molar mass to convert it into the number of moles. Then we can apply the mole-to-mole ratio. And then depending on the type of information that they want for whatever the second chemical is, and that really depends on the state symbol. So you're really going to want to pay attention to that. If it's AQ, that's going to be a liquid, and if it's S, that's going to be a solid. Well, if the second substance is a solid, it's a no-brainer. Straight across this lovely little table that I've given you. And then you can convert from moles using the molar mass back to grams. Well, what if the second substance is actually a liquid with the state symbol of AQ? So once you reach the mole-to-mole ratio, instead of continuing straight down your path, you could actually kind of veer to the side a little bit using a molarity number to be able to convert back to liters. In like manner, what if the material that you're given in the beginning of the problem is a liquid? You'd start off with your liters and then use your molarity to convert it into moles. Once you're in your mole-to-mole ratio, if your second substance is also aqueous, you can use its molarity to convert back to liters, or if your second substance is solid, you can use an alternative pathway to get back to the measurement of grams.